Wait, hold on, I'm doing it. Oh, yes, Peter about it. It's like I yeah.
My wife is on that list.
Yeah.
Oh,
I don't think that there's like.
Hi, everyone. Welcome to today's session. It's my pleasure to introduce Professor Devavrat Shah, who is a professor in EECS at MIT. And he has worked on a lot of very interesting problems, I think more recently on causal inference. And he has also done like amazing work in terms of like algorithms for data, in particularly keeping like human and society in mind. And the list of awards is like quite long. His works have gotten like lots of best paper awards, test time awards, including going back to like dissertation awards from his like PhD. And so we are super excited to have him today, and he will tell us about inference and algorithms. Right? So take it away.
Okay, Ravi, first of all, thank you for having me. Really appreciate it. Lovely to be here back again. You know, my first conference ever as a grad student or as an academic, as a grad student academic, I was actually in Wisconsin in 2000 somewhere, and I just have a lovely memory of that. So dying to be here and go back and see the lake. Of course, it won't be as warm, but you know, warm enough, given that I'm coming from Boston. So thank you. As there is a sort of efficiencies in the air, so to speak, everywhere in the news. So I thought I will be also efficient and change title of my talk a little. And instead of just talking about one algorithm, maybe I'll talk about two algorithms. So just in case, if powers to be are looking at the recording, they will see that we've been very efficient. But jokes apart, I thought that I will spend some time talking about one of the algorithms that was a primary driving contribution behind the primary topic of that was advertised, and the second one, which has been very much, as I would call, fresh off the press. We just posted it on Archive, and very exciting. And again, it's simple, and some of you, including you, Dong, have worked on the topic before. So I thought it would be great to get feedback. So with that in mind, we'll talk about two simple questions. And two simple algorithms and proofs for them. Okay, so let's see. It's a little bit of ambitious agenda, but I'm hoping that I'll get through it. Please feel free to stop me anytime. Ask me as many questions as need. First part is primarily thesis of Abin Shah, who's now graduated and on the brighter side, working at a hedge fund in New York. And this second topic is with Yasser Jedra and Emily Khan. Emily is an undergrad and Yasser is a postdoc, and very much driven by Yasser. Okay. So what am I going to talk about? Two things. First, I will talk about algorithms for learning exponential family. If you know exponential family, you know that sort of is the bedrock of all sorts of modelings we do. And maximum likelihood is an amazing estimator for that. The only challenge with them is, in general, when you think about maximum likelihood, it's computationally hard. So really, what I'll talk about is a very simple algorithm, which is effectively like maximum likelihood in all sorts of properties, but it's simple, it's clean, and we'll talk about the proof, why it works. So nothing complicated there. Now, the way algorithm is structured, it also extends very nicely for the setting where for one, for let's say high dimensional distribution, you're observing only one sample and you still want to learn the parameters for it. You could use it to do that, and that has a nice implication. That was the part that I was originally planning to talk about and I'm not discussing. But I think this is a good start. And instead of talking about this, I will talk about just a classical question of computing SVD or KSVD, the top K components of matrix or singular value decomposition, and talk about gradient descent for it. And that always works. It's super clean. There's no sort of model dependent tuning, this, that. And turns out it is exactly, at least in simpler form, it's exactly like what we might remember from our high school, called Heron's method, Babylonian method. You know how if you give you number s, which is positive, and I ask you to compute square root, what is the iterative algorithm you would write? That's exactly what it is. So we'll walk through that. Once we do that, then you can do acceleration too, and some really nice things happen. But again, still figuring things out. So I will just talk about as much as I can there. So again, that's the agenda. Likely I'm going to spend 30 minutes or so here and 15 minutes or so here. And again, you'll keep me honest with questions. Okay, so starting with learning exponential family. This is the manuscript that covers this topic. I'll start by just reminding us what the exponential families are. So if you have seen it before, my apologies. I'll talk about the maximum likelihood estimator for it. We'll just walk through simple calculations with simple example, and then I'll introduce the different estimator, and then sort of see at least in action for one example, and then spend a few minutes discussing why it works, and then there's a bit of a proof. So that's the plan for this. So one way to think about exponential family, you've got some domain, an element of domain, let's call it small x. Some feature f of x could be multidimensional, and parameter is theta, so it's a theta transpose f of x, determines effectively the probability of x through the exponential transformation. And the z is my normalization constant, so that sort of things integrate, and it actually is a probability distribution. Nice, simple, classic example is Bernoulli. Of course, if you're from queuing world, then you would talk about Poisson, but Bernoulli is a simpler one. And again, parameter is lambda, and its moment is the mean. Okay, and as we know, there's a nice intimate relationship between these things. In particular, parameter is exactly equals to this as a so far so good. Okay. The learning question that we are interested in is going to give you an IID sample from this distribution, and I'm going to learn the parameter. So I don't know the parameter theta star, as per which from which this is sampled, and I want to learn that. The context of Bernoulli, of course, we are seeing NIID coin tosses, zeros and ones, and we want to learn the parameter. But again, I don't need to make it super complicated, but for the purpose of ceremony, I will do that so that we are on the same page. All right. So maximum likelihood, we'll say, well, compute the likelihood of these observations and then find the parameter that maximizes the likelihood, or log likelihood. And again, in this case, log likelihood would be the log of, so because IID, product of these likelihoods, log of that is the sum of the log likelihoods. Logs remove exponential. This is common, so it sits here everywhere. And since we removed exponential, we are left with this. So that's my log likelihood, and I'm trying to maximize it. Well, going back to our example, my log likelihood maximization would look something like this. Okay, and again, here I've done this, replaced it by mu hat, which is empirical mean, because as you can see, I can take this thing out, then you get 1 over n times. So it's an empirical mean of my sufficient statistics. And that's what has happened here. Okay. And this is just a log of my normalized. Let's set it to derivative to 0 and solve for the equation. And as expected, we'll do what we started out anticipating with. That is, lambda is nothing but the log transfer. And we can do the similar thing here, where again, the hope is that find theta so that the moments under that distribution matches my empirical moments. That's the moment matching. So just to, you've seen this before, I know it's boring. If not seen, I think it's pretty remarkable. First time I saw it was remarkable. Okay, and you know, if I give you a large amount of data, of course, this would converge to the moments in the true distribution. And so I'm trying to sort of match that, and under reasonable conditions, we know that sort of this indeed, as n goes to infinity, will get the conversions. And that's what's happening here. So far, so good. No questions so far. All right, and again, beautiful properties of MLE. It's consistent. It is asymptotically normal. It is efficient. But the Z makes it hard, especially when sort of the models are not straightforward. Then D can become computationally hard, and they're also subject to computational hypotheses. Correct? I think this will be hard to compute in general. And then maybe if I want to go to n equals to 1, what can I do? And again, when I go to n equals to 1, one might ask a question, are you thinking about a coin toss or something interesting? I'm thinking more like the classical linear system, where parameters are repeated multiple times, right? So I've got one trajectory that I'm seeing, but parameters are repeated across time. So really, that's what I'm trying to think about. So some form of repetition of parameters across space, but it may not be sort of just exact repetition. It might be in some other form. That's a type of thing I'm thinking of. Will not get that here, but happy to talk offline. Okay. So really, ideally, I want to retain these things and then sort of get this, and maybe then go to this. That's the goal. Okay, so here's a function. Here's an alternative estimator. So again, this is what we're trying to, we have a distribution and we're trying to find parameter. And the claim is that I'm going to minimize this loss function. So let's parse it a bit. Actually, parse it a bit with this in mind. Okay, so if I look at likelihood, it's a product that I've got sum. That's one cheating. I got rid of Z. That's 2. And then I kept this, but I added negative. That's 3. So those are the 3 changes. Okay. And the argument is that it should do well. Of course, if I have a prior information about where the parameter come from, I'll put those constraints. If constraints are nice, problem will remain nice. And for me, it takes a while, but for some of you, it will be obvious that this is a nice convex minimization. Okay. So the few questions: why should it work, and what are the conditions we need, etc. So one condition that I will require is that for the purpose of arguments that come from bounded domain, if it doesn't come in exponential tail, argument should work out. Second is that the sufficient statistics that I have, I know that sort of it integrates to, or I can compute its integration over the domain with respect to some known measure. Okay. For the purpose of presentation here, I will assume that this function, when integrated over domain with respect to uniform distribution, it is a vector 0. So that's a key assumption in my mind. There is the sufficient statistics is such that when I integrate it over the domain with respect to a known measure, here I'm going to use known measure as uniform. It integrates to a constant, which I can subtract, and hence it's 0. Yeah.
Does that measure be related to the other one? Hate the other one or anything?
Okay, so so we want sort of same support.
Need that.
Yes. Yeah. Here I'm going to assume uniform. So actually, let's ask a question: is it really good? And best way to do is again go back to the same example and see what happens with that example. So the first thing I will do is that to make my my function was x there, right? Now, since an x takes values 0 and 1, to make it integrate to 0 over 0 and 1, which is half, I will subtract half of it. So now I've centered. Centering doesn't change much, but now I'm looking at sort of finding lambda that is minimizing that quantity. And if I have enough samples, effectively, this empirical mean is the mean with respect to the underlying distribution. So I'm computing this. And now if I write it down and not make errors, this is how it would look like. Okay. And then I look for minimizer. Minimizer would have this equals to 0. And I set this equal to 0, then I'm back to exactly assuming same thing. Okay, so at least for this case, this works. Okay, so at least with an example, we're convinced that this is not doing something. Now the question is that why should it work in general? Okay, any questions? It's a nice problem. It lends itself to all sorts of iterative algorithms. I will not go into that. One can analyze carefully. I'm going to just talk about this, arguing that this is a proper loss function that is indeed, with enough data, it finds the right answer. There's all sorts of finite sample thing that I'm going to say, but I will not know. So let's look at that. Let's argue that it is a proper loss function. Again, with enough data, I'm looking at something like this. So let me understand whether asymptotically it's the right thing to do. And the main claim is this, that we are trying to minimize this. Okay. The minimizer of this, or the argument set of this, is same as argument set of this. Right, so that's what we are minimizing, or a bit large amount of data, that's what we're minimizing. The minimizer of this is same as minimizer of this. And why is this good? We're trying to minimize scale divergence between uniform distribution and this parametric distribution where it's a little twisted. So originally it was p theta. Now I'm doing p of theta star minus theta. If I want this to be minimum, I want it to be those two things to be equal. And if I want those two things to be equal, that'll happen when this is p0. Because the way exponential family is when sort of in theta star minus theta transpose, if it's 0 transpose, then no uniform. It means theta is equal to. Okay. Right. Yes.
Is this like the argument theta, the KL, is this different than saying if you were to say KL of P theta star and between those two distributions?
Wonderful.
It's implying the same thing.
No, good. So, if I may paraphrase, what you're saying is that we know that maximum likelihood, one way to think about it, is actually we are minimizing KL divergence between P theta star and P theta. So what twisting is going on here, right? And I'll come to that in 2-3 slides. There's a nice relationship between, there's a surrogate function coming from fragment divergence and all that. On one end of the spectrum, you will get MLE. On another end of the spectrum, you get this. Everything in between, we don't know. As in, I'll talk. Okay, so now my goal for this part of the talk is just to convince you that this is true, and then we're done. Okay. So let's walk through the proof. Okay. Okay, so this is the most complicated part of the proof. So let's do this. So we're looking at the same distribution, okay, but instead of theta, now it's this parameter, and this is just my z. Okay. And if I do the z theta star properly and take this part out, then I get this sitting here. So I'm dividing by on both numerator and denominator by z of theta star. So I take this out, divide by that, I get this. Similar thing I do here, I get this. And of course, the remaining part is this left, and the remaining part is this left. Right now, this is exactly taking expectation of our loss function with respect to the original distribution, which is the quantity of our interest. Okay. So far, so good. Now let's just write down this KL. So this is what I'm doing. So that's now we replace this by p theta star e to power, and then this is expectation of L. Okay. And now sort of we'll just take the sum of the logs. So that's the first term. Okay, that's the second term of our interest, and we want to effectively say that everything else is now useless. So if KL and this and everything else is useless for the purpose of minimization over theta, we're happy. So this one, and this is where I'd carefully chosen this to be, if I take the theta out, then expectation of U of f. And as you remember, that was the choice we had made. So it's 0, so that's gone. This term has nothing to do with theta, it's constant. Which means that now minimizer on both sides does the same. And I'm done.
Just want to make sure I understand. So
yes,
are you assuming that x's are continuous?
or
If they're discrete, do you use a different measure than uniform? Or do you always use a uniform over the domain, whatever. So it could be discrete too. Okay, gotcha.
Okay, so then we're done. Now this is coming to your question. In a sense, we somehow avoided Z, and so the question is why. And again, it's a work in progress. So I'll sort of tell you what we understand so far. And yeah. Okay, so this was the true distribution. And what we did instead, effectively, we looked for this centered version. That is, set it to 0 so that it was centered. And that has effectively this form. Okay. And in some sense, in the process, what happened is that we went to centering. Somehow these two things got flipped. The expectation of exponential became exponential of expectation. And that's what led to that versus this. Now, that's kind of an algebraic explanation. Don't know exactly what's happening. There was this very nice work that came out of a few other groups looking at different types of surrogate loss functions. One of them was based on Bregman's divergence and nicely parameterized by alpha. Turns out, at least in form of algebraic limit, not the method limit, but algebraic limit, this becomes this as alpha goes to 0. And this becomes this as alpha goes to 1. So if there was any justice out there, what should happen is maybe there's an alpha star, and on this side, maybe computation, you're efficient, on the other side, you're not efficient. Right now, we only know that this is efficient, but are never else. That's as much as we understand. Okay, so what I've done is for generic exponential family, if you have a sufficient statistics that you can integrate over the domain with respect to your favorite known measure, you can massage it to actually come up with a method that is computationally efficient. I showed you consistency, but to turn the crank, because it's actually also an M estimator. So for example, out of Amemia 1985, you'll get all the asymptotic normality. Try to figure out whether we lose efficiency or not. We do lose. So there is one counterexample where we know that sort of, in some sense, it's factor 2 off. I don't know how much off it is. Is there sort of a bounded constant? Does it work with all sorts of interesting questions if that's the type of things you're interested in? Maybe that's where sort of the trade-offs are happening, that computation and performance, because MLE is efficient. We got this one.
Interesting. On the efficiency things, it definitely was within a factor of 2.
At least lower bound. Define an appropriate way. And there's a simple counterexample.
Yeah. Oh wait, you mean it's at least it could be more?
It could be more,
I
absolutely.
see. I thought it was within a factor. It's not
No, it's not upper bound. It's a lower bound.
Okay.
We just have one counterexample. And in general, does it become worse? And of course, finite sample guarantees follow similar machinery. So nothing really new there. And in a sense, you will get 2 norm error, for example, will scale with appropriately defined dimension of the parameter space and 1 over square root of n, as you would hope. For example, if we restrict it to sparse graphical models, which is one of the things that has been always driving me, let's say it's a degree D graphical model, and I don't know what the things are, then this would exactly scale like the log of number of variables, and it'll have the right dependence on the degree and all that stuff. So in that sense, it matches the best known bounds we know for graphical models. So I don't think this is inefficient in the sense of rate of convergence and all. Okay.
Question: is it so in general? Is that just maybe a constant factor, or you're saying conjecture?
Conjecture, because we don't have. Because I think there's some log factor or square lurking there. That's why it's like not for the CLT. Okay. Yes.
Just a quick question. It's more minor, but so for function, so based on what you wrote there, if we were approximately solving the problem as stated, then we would need a guarantee in terms of distance to optimum, which we get for problems like this with methods that are polynomial time but can be quite polynomial. On the other end, we have so this is, if you take log of this, you get things we know how to work with, but we only get the approximation in terms of the value of the loss, not in terms of the distance. And I'm wondering whether that would still be useful.
Good. So there are lots of things. So maybe if you have finite number of samples, you're running, let's say, some form of some iterative algorithm on top of this to solve that optimization problem, how far it is from actually true thing. So these things, at least under reasonable condition, will have reasonable curvature. So it will allow you to bound things. And that curvature would depend on the problem setting. So there is things that we've explicitly worked out in the paper.
I see. Thanks.
Great question. Okay. And what about n equals to 1? Again, so there is, if one defines it sort of at least the parameter over high dimensional setting comes from some form of, uh, some known space where metric entropy is small, then actually you can sort of learn it from one parameter itself. For example, let's suppose that I've got an Ising model with one unknown parameter, then one sample is. Or I have sort of enough variation happening still in an Ising model per edge, but the variation is not too bad. Then again, so one sample should be enough. And that one required a lot more work. There's a nice Sobolev inequality that needed to be argued there to establish certain curvature properties. And then we got to that because of looking at causal inference setting where counterfactual distributions are modeled as an exponential family, and the part of unobserved confounder are changing the exponential family parameters. So in a sense, you've got many samples coming from same family of distribution, but each sample has a different parametric representation. And so now you want to learn across together. And that's why this was very useful. And that nicely generalizes all sorts of panel data literature out there and a little bit more. That was originally what I was planning to talk as in the remaining 15 minutes, but I will switch that. Look, it's okay. And my apologies if you came for that and I'm not doing it justice. But hopefully this would be interesting too. Okay, if no more questions, then I'm going to move to the next topic. Okay. So KSVD, again, for the purpose, let's think of nice symmetric positive definite matrix, and I want to find the top k-cup. It's a classic problem. And as we know, there's a lot of literature. This is the oldest, at least, paper we could find. From the Sobolev was 1929, so like 96 years ago. And then there was Lanko's, then QR method somewhere in between. Then, of course, the Golub's work at Stanford on all sorts of nice numerical linear algebra. Somewhere block Lanko's is people started doing rate of convergence in 80s, right? Not that they were not done, just now people started explicitly writing down. And then even 90s has been very active along the same line, and I think it continues to be. There are lots of other nice random projection-based methods and so on and so forth. This is just a beautiful topic, continues to be evergreen. So the question is, why revisit? I mean, one answer is why not? But that's not a great answer. For me, I was personally interested in is because trying to understand how do we scale sort of SVD computation if you have to scale? And there are all sorts of interesting approaches out there. I want to get very large matrix and I want to compute its SVD. Now that everybody has built beautiful optimization infrastructure, why not just use that? So if you write down a great algorithm that's gradient descent-like, then you just throw it to existing optimization infrastructure. Intellectually, there are lots of nice work, especially over the last decade, that has happened where form of whether it's a matrix completion or non-convex objective associated with SVD has been utilized to understand harder problems. So this has been a good sandbox where theorists can do certain things, sort of argue about the phenomenon. And again, so it's one of the base procedure for things like matrix completion. So those are the three reasons why we are interested. We can agree to disagree on the reasons. I think as a topic, I think it's still very interesting. Okay. Okay, so now what is the optimization problem we are solving here? So if I want to compute, let's say, leading eigenvector, for example, that's the right-hand side is one form of a variational representation. This is another form of variational representation. I'll focus on this one. That's the one that one would use for typical power method, right? So here is the gradient descent. So again, I'm going to sort of try to compute the leading eigenvector. So that's my objective. That's my gradient. Do random initialization. Let's say Gaussian with mean 0 and identity as my covariance matrix. And then we'll iterate like this. So I'm setting everything, right? So my iteration at x time is this, minus this is my step size, defining it. And this is my gradient. If I define that, then that's my gradient update. Just to contrast it with power iteration, it will do something like this, right? So again, whatever I had before, I apply, normalize by this, half at that map. Okay. And the claim is it works. Okay. And roughly speaking, here is what happens. There is a region around where the answer is, which is nice contractive. Factory like a, so there is a sort of linear convergence within that region. And to get to that region, you will always get to that region within some amount of time. So that's maybe sort of rephrasing it. The time it takes to get within epsilon would depend on the gap, as one would hope. So 1 over gap and log 1 over epsilon. And why this works, so there's of course, this proof, it's not super complicated, but I think the reason we got to that is because of this literally silly pattern matching. So I'll walk you through pattern matching because that was helpful. Yeah.
So I was wondering, like, in the settings where you have the first two eigenvalues having like the same magnitude, would this reach at least the subspace spanned by those with like say sigma 1 over sigma 1 minus sigma, like the next, would it, or does it just like fail somehow to converge at all?
Good. So our proof would not be able to argue that difference right now. Numerically, what we have found is it works.
Okay.
So, yeah.
Okay.
Yeah, I was just wondering, I mean, maybe you're going to get into it after this proof sketch, but it's, here M is formed in both the power method and the gradient method use applications of M, right? But if I were thinking about a huge data matrix, I don't want to even form M. Does the gradient thing help then? Is that the idea?
Yeah, so the hope would be that so then you would distribute the gradient.
Yeah,
exactly. And then sort of so if this doesn't work, that won't work.
Yeah, gotcha. Yep.
That's a hope.
Yeah.
A question?
Yes.
How important is M being positive semi-definite?
Not really, because if you want to compute SVD of M, you will do MM transfer or M transpose M, and then.
Oh, but if M is have negative values, is it possible just?
No, so then this proof won't work.
Oh.
So you will have to do MM transfers or M transpose M.
Okay.
Okay, this is just one. So again, this is a non-convex setting, and of course, it has a saddle points. These are local minimas. These are of course, symmetric global minimas. Signs, and this is just showing if you start here, you will go there, or you start here, you will end up with. I think this one actually started from here, went there, and then. Okay, so that's the relationship. This is what got us started. So ignore that for a second. I'll just remind you of this. This is even the Wikipedia page on this is very nice. So let's say I've got S. I want to compute its square root. The Babylonian or Heron's method says that, and there's somebody from India also who is apparently, as per Wikipedia, attributed Bhanumashali or something. Okay, but goes like this: xt plus 1 equals to half xt plus s over xt. If you think of xt equals to 1 plus epsilon t times s, so where epsilon is the error, multiplicative error, then what will happen is a part of this iterate, you would be able to argue that epsilon t plus 1 is less than or equal to minimum of epsilon t squared divided by 2. And the second one is epsilon t divided by 2. So if epsilon t is large, you're increasing at a linear rate, so it's like 1 over 2 multiplying. And once epsilon t becomes less than 1, then you're going double exponential, it's like a quadratic. And that's how you will converge. Now let's see what's happening there. So with these kind of things, you always assume simple things. So we assume matrix is rank 1. You think of matrix rank 1, so it looks something like this. Okay, you replace that into the gradient update, and you get this. And really, in the rank 1 case, all you really want is xt to converge to the right singular value, which is the square root of this, because then it's square root of sigma 1 u1 transpose square root of sigma 1. That's where you want x to converge. And that's what's happening. Then question comes, of course, what happens when you have other components and so on. So that becomes a little involved. Okay. Right now, once you have this, and you say, okay, so now what can you do? Because this is the premise that if you can do this, then maybe more interesting things that the optimization world has figured out, we can try to apply and see if something interesting happens. The first thing is, okay, this is the experiment saying that with gap, it decays like this. And we say, can I sort of make it sharper? An acceleration method would try to say maybe my dependence on gap should reduce. And here is, for example, Polyak's acceleration applied. This is what power method or this method would do. And this one is what the acceleration looks like. So as you can see visually at least, in this much amount, this goes similar amount. This one goes half the. So you get 1 over square root of gap. Yeah.
Where would Lange's one?
Sorry?
Where would Lange's?
I think Lange's has a faster version than sort of.
So it also achieves acceleration. But
Yeah.
I'm just wondering if you tried comparing to it just numerically.
So again, so this is all ugly. So I have to say we don't have a good detailed comparisons. Like we haven't even put out how Nestro's acceleration would look like, because given that sort of there's an attractive region, you can argue that borrowing existing proof that Nestro's would work, but at least numerically, how does it look like? Don't have good things. And how would the stochastic version of this look like? These are great questions. Right. Well, that's as much as I have to tell. There's a long literature on this, by the way. We're not the first one to look at this from this perspective. So I'll just briefly point out that and end the talk. That's
Sorry, just one more question. So for the step size, I missed it. Sorry, in your results. So what do you require from the step size to get this complexity result? Just 1/2?
Yeah, just so 1/2, and then it's normalized.
I see. So there is no
There's no
kind of
tuning.
need to search for a step size, but then why do numerical experiments have different thetas?
That was just to sort of say how things change. But sort of half turns out to be the right thing to do, even numerically. Yeah, I mean you could. You could add eta here. But our recommendation would be just use this.
But the analysis works for any constant beta, anything between 0 and 1, and bounded away from 0, 1.
That's correct. It should be between 0 and 1. Yes. Yeah, I think, yeah. Yes.
Thinking about the parents' method, like what if I had S was a sum of a bunch of things, and somehow I wanted to compute the square root of the sum, but I'm going to somehow use individual pieces, which would maybe be analogous to the SGD thing. Is that the case at all? Like, yeah, I would, because you won't, you don't want to have your whole n, right?
Yeah. Yes.
I wonder, yeah, I'm just wondering. I mean, people do SGD, but they say that, and it works, or
We've not done it.
uh,
Okay, so if, first we were trying to understand whether this would work.
Yeah.
And kind of, given we being paper pencil person, first we were to see it working in paper pencil.
Yeah.
So it's kind of an opposite route. Well, I think they're all next set of questions. Maybe I'll sort of spend 2 more minutes on this, or 3 more minutes on just literature, and then. So lots of interesting results. For example, there was this sequence of works that came out in close to a decade ago, try to explain the fact that there are no spurious local minima coming from matrix computation literature. I think in some sense, some of these results were start of these kind of analysis. Then was this specific problem. There are lots of nice work that came out, work which argued that with right initialization, there's no convergence that happens. If you're trying to compute, if the true rank is D, but you're trying to compute K approximation, let's call that over parameterized with initialization, then there is a work, actually Yudong and his collaborators, where right initialization for all K, precondition local convergence, the precondition local convergence with, there's lots of very good literature here. This one, for example, in some sense, pretty close to what we've been looking at, but then it requires lots of problem-specific parameter tuning. And then there is this is another recent work that came out. So it's a pretty active area. And it's likely that we have missed some because we've not been active into this domain. So if you know something that I've missed, please feel free to point it out. All right, so with that, thank you.
Questions?
Yeah, I somehow missed in the last part. So what is your result for mixed integration? Because you're solving what rank 1 question in.
So so this one would work for any rank K.
I see. So the proof just works for any rank.
For any rank.
Okay.
Sorry, I did not complicate the main result. Yes.
Okay. Thank you.
So you could have sort of original underlying matrix with, for example, full rank, and you're trying to compute rank K approximation, just the way power iteration would sort of try to peel things off. This would naturally peel things off.
I see. So okay. So it's not like you would use directly this algorithm, but you would just
Build it up.
dealing like okay. Thank you.
going back to the first part, something is like an easing model.
Yes.
Does your approach solve or help with any problems in statistical physics, like in quantum or something? Is anybody think, hey, great, we can do something we wanted to do in a simulation that we couldn't do before?
So,
like physicists we're obsessed about the partition function. I did all sorts of ways to try to approximate as to what you've avoided, but that helps them.
So the interesting question that you're asking is that there is two parts here, right? With learning the model and then sampling from the learned model.
Yeah.
This doesn't help with sampling, right? It helps with the learning. And someone can ask a question that sort of is learning enough? So for example, here is where it's really enough and here is where it's not enough. So there's a very large high dimensional setting, learn model. Now, given that model, I want to, given observation of, let's say, p minus 1 variable, I want to infer pth variable, or given observation of p minus delta variable, I want to infer delta variable. This would be efficient, but not otherwise. Because it's exponential family also, and as we know, conditional also have exponential families, you could actually learn conditional distribution. And the way you do that, you learn conditional distribution for those d variables that you want to infer, subject to everything else. And then use that to sort of factory do that simulation. So it'll be small. And that could be very helpful. But if you're now to sample all p, now you're in trouble. Yeah. So it's kind of it half solves the problem from that perspective.
Well, one good question about the first part. It kind of reminds me of the exponential loss that people use for binary classification, where instead of logistic loss, also use exponential.
So yeah, it is some form of a surrogate.
So then you can say something about like how to handle it loss by this kind of.
I guess, for example, here is what you could do, right? If you do logistic regression, if p is very large, it's also a maximum likelihood estimation. It's not straightforward. Now, it's a large p. This one would say I can do logistic regression
with the exponential loss.
With the whatever loss I was showing.
That's the exponential loss.
Yes,
right. I think.
So actually, that's an interesting point. Because of if you're trying to learn the parameters for logistic regression, you would do effectively moment matching like algorithm, and this would replace that, and this would be a lot more efficient, assuming that p is large then.
Any other questions? Yeah.
For the first part of your talk on exponential family, I think it would be pedagogically interesting to see what your findings say about the gamma distribution. It's usually the sort of the first example we see when we teach maximum likelihood estimation that doesn't have a closed form for both of its parameters, yet it's a 2-parameter exponential family.
That's a good question. Nobody has asked me this question, so I will do my homework, or maybe I can correspond with you. So I don't have top of my head any answer. It's gamma. Okay.
So I have a question about in the first part of the talk when you commented on the like the n=1 kind of thing, like where you could potentially have observations that are related to theta. Like I was trying to get a sense of like, can you maybe tell us a little bit more about it? Let's say I have like like nodes in the graph where I'm observing things, like what is the assumption that goes into? Is it coming from like same underlying theta somehow? Or
So let's suppose that I've got p-dimensional settings, I've got a theta, but I'm going to tell you that the theta1 to theta p, collectively they come from a space where norm of that vector is bounded above by 1.
Okay.
So now it's actually, it doesn't scale with p, it's actually constant. Now I'll give you the whole sample. Actually, that gives me a lot of information because now I've got p bits of information, even if it's 0, 1, right? In some sense.
I see.
And now I can sort of use that to learn it. And this objective actually nicely separates it and allows you to do that.
Oh, interesting. Okay.
So it'll learn just from 1. And then if you have multiple samples from related different parameters but same family, there's some relationship between them. Let's say these are only, take a very classical view of there are only k different types of parameters that are there. I don't know which ones are. So That's another sort of low complexity setting. And then I would be able to learn them simultaneously, even though each distribution.
Thank you.
And like classical linear system, right? Like autoregressive, like xt plus 1 equals to axt plus Gaussian noise. And then in this case, the parameters are the same across all time steps. So even though I've got one trajectory, my parameters are same, I should be able to learn a lot, which is what happens. So that would, for example, be an example of it.
So for that, the k different kind of like thetas being like potentially distributed, let's say on key points. Would the rates for it, for example, for the Gaussian?
So then it will depend on sort of then in some form of metric entropy of the space, uncertain space that you don't know from which you're trying to pick. It'll depend on.
Okay. Thank you.
Of course.
Okay, so I guess let's thank the speaker.